Good afternoon. Thanks a lot for your attention. My name is Stephen Boyd. I am an entrepreneur. I am a fluorine chemist. Most of my PhD work was actually on rare earth-doped fluoride salts. That's actually what I'm going to be talking about. They were discovered as early as 1803, and they're not actually that rare in the Earth's crust. The reason why rarity was attached to it is because, as Bradley had indicated in his talk, they're rather diffuse in terms of their prevalence in the Earth's crust around the planet. Placer deposits, they're minor. Monazite veins and churchite veins are actually the major sources of rare earth elements. Monazite is highlighted here because of the co-prevalence of thorium that co-occur with other rare earth elements. Churchite veins, more dispersed. They were found actually originally in the Schwarzwald region of Germany, but there are several very concentrated locations around the planet, most prevalently in Mount Weld in Western Australia. They're basically grouped by lights and heavies. Churchite is actually a general name for the mineral, whereby you have lots of different types of rare earth elements, mostly the lanthanides, which actually occur quite specifically, and again, they are phosphates. They are phosphates, very similar to monazite. They were actually really difficult to isolate. They have extremely high melting points, they're oxides, and the metals, the base metals themselves, when reduced, have very, very high melting points. Those were two contributing factors that actually made their isolation and characterization very difficult. And so one of the major advances to get them out in much larger quantities was actually developed in the 1940s by a Canadian. I know we have a nice solid Canadian presence here, a guy by the name of Frank Spedding, and he developed the ion exchange matrix. This is a crystal structure of one of the first clays that was actually used in order to perform ion exchange, called montmorillonite. These are actually atomic positions inside the crystal. What makes this so interesting is that the aluminum, and in both these positions, represented by the purple and red spheres here, are both +3. They're both +3 oxidation states, and they relatively easily can move in and out. That's a hint. All of the rare earths are in a +3 oxidation state when they're oxidized. And that's why this worked to such huge advantage, actually, for the Allies in the 1940s and then subsequently in the 1950s and 60s. And I'll get to the reason why it became even more important as the nuclear age came into its own. How do we identify these things? How do we do it? We actually use X-rays. But they're powders. But that's okay. Because look what happens. If you shine an X-ray, series of X-rays, and you move the X-ray ever little so slightly, ever a little bit, you end up hitting these planes. When you hit these planes, something special occurs. You get reflections. You get very intense reflection peaks. That's how we identify what crystals we're working with. Phosphates, oxides, nitrates. That's how it works. And each one has its own fingerprint, and it is based explicitly on taking X-rays, beating the heck out of your sample with some X-ray, like I did at the National Light Source at Brookhaven National Labs. And that's how it works. It follows along these crystallographic planes, these tetrahedra and octahedra. And when you hit it, you get an intensity. And you notice, well, this is actually a poor representation. It's actually represented in 2 theta, 2 times the angle. What happens regardless of the nuclear process? You get a lot of fission products. And we know what those fission products are. There's the so-called rare earth. Chemists and physicists got a hold of these things because it was the first time they were able to simultaneously isolate them and have the financial wherewithal and the equipment to be able to dope them, to be able to put them inside very simple crystal structures and then analyze what made these lanthanides and actinides so special. This was playland for chemists and physicists in the 50s, 60s, and even into the 70s. And I met some of the original scientists that did this. They literally would take a hot samarium or a hot erbium, literally dope it into a crystal, grow the crystal, and then the experiments they were running were called electron spin resonance. They would literally put an erbium or a terbium or ytterbium right into the center of a very simple crystal structure, the structure of which they already knew, like I said, with X-ray. And then they would look and they would excite it very precisely and see what would come off. And they would do it because of the electron spin. And you may ask, well, why is this so important? Why are the rare earths separate from the rest of the periodic table? It's because of their electron configuration. This is probably the best periodic table I think I've ever seen as a chemist. Why? Because it groups the elements, all of the elements in terms of the periodic table, it groups them by how we as chemists and physicists count the electrons. They are dominated by the s orbitals over on the left, the d orbitals in this broad structure in the middle, the p orbitals over on the right, and this is why lanthanides and actinides are so important, is because they have f orbital electrons. And that is what brought modern electronics into the golden age, which we are in right now. Here are the rare earths. Okay? We have the lanthanide series. We have the light rare earths. I'm going to talk explicitly about the 14 rare earths in the lanthanide series and, to a lesser extent, the actinide series. We have the s orbitals. We have 3 p's. We have 5 d's. And we have 7 f's. And exactly 2 electrons only can fit in each orbital. Only 2. But 2 times 7 is 14. There's your 14. If you recall, 2 orbitals times 5, it's 10. That's the trick. There's a second trick. The Aufbau principle, yes, that's shameless self-promotion. My company is called Aufbau Laboratories. There's a very specific way in which the electrons add, element to element to element, as you go up in the periodic table. They add 1 electron at a time in each of those orbitals that I just showed you. Up, 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 okay? And there's 7 of them. So if you look at the periodic table again, look at number 7, right in the middle, gadolinium. It means that every single one of these 7 orbitals has exactly 1 electron in it, and they're all pointing up. And that's a hint. I'm going to allude back to that in just a minute. This is how they add. And let's watch. It's just simple counting. 1, 2, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. 5s, 5d, and look at the arrows. So it's 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. Oh, look, it goes back to 4. Well, everybody knows that 4 is less than 5. Okay? That's another hint. What is so special about those f electrons? Well, as I just pointed out, 5 is bigger than 4, right? So look what happens. When you excite one of those f electrons, it goes up into a higher energy, into the 5d. But the second that it gets up there, it kind of doesn't like it. And so it drops back down. But you can do that all day long. What makes this more interesting? What did I say? The 4f energy is actually more numerous but lower in energy. If anybody has taken art classes, historically, all of the colors that we see in Monet, Manet, Pissarro, they were all made with colors right here. Why? Because we can see those colors. So what did we discover in the golden age of atomics as they were moving forward? We figured out that it took relatively low energies to excite those electrons into those empty d orbitals and boom, drop them right back down into the f's, because that's where all those f electrons are. Very interesting. What does that allow us to do? It allows me to make this laser. I excite the electron up because I know I'm tuning my crystal, because I know what element I'm going to be doping in. So I can tune my energies, And I can make red laser light. If I go a little bit higher, I can make green laser light. If I go a little bit higher, I can make blue laser light. Because I now know what those relative energies are. And they're all, almost exclusively, they're all in the UV-Vis band, in the ultraviolet visible light band. Now, that is really important for us. Why? Because every single one of us has a cell phone in here. And we need to communicate that light, that electromagnetic radiation, very specifically and very reproducibly. And so that's why they are in satellite guidance systems and our cell phones and our computers. And because in addition to visible light, we're trying to very precisely control electromagnetic radiation, stuff that we can't see but is nevertheless light. Same stuff. And that's what makes these things so special. If you recall back to high school chemistry and physics, look at where these wavelengths are. 425, 325. Well, this is in the violet/UV band, and 425 you're pushing right into blue-green. These are very useful colors for us. Note, too, the wavelength distribution is actually rather narrow. And we can tune that further and further and further so that we can, in fact, get neodymium-doped lasers. Electrons are adding spin up, spin up, spin up. One electron per orbital. And they're all pointing in one direction. That's how magnets work. That's why if you ever take a kitchen magnet and you break it, it's still got a north and a south. Because you haven't changed the direction of the electrons. They're still all pointing up. That's how magnets work. And when you have, per mole or per gram, a lot of these that work well with other what are called high-spin metals like iron, like cobalt, you have fabulous punch. You've got a lot of magnet in a very small size. And this is an excellent article that was published in 2009. It's the Journal of Magnetism and Magnetic Materials. So that you've got terbium, you've got gallium, and you've got iron in there. You have fabulously, and look at the layers. Light is basically an electric field and a magnetic field at right angles to one another. You can control this. That's pretty interesting. You can control this. You can flip the spin. You can temporarily change that magnetic field from one way to the other. That's what makes lanthanides so special, and rare earths in general so special and so strategic. Because you're controlling a satellite hundreds of miles away in the vacuum of space-time. You're sitting comfortably in front of your laptop in your lab. You can't be up there. But you have the ability to control these things from very far distances. Why? You're using electromagnetic radiation. That's how you're sending and receiving these signals. And that's why the applications of rare earth elements they're so important, they're so ubiquitous, and they're so important to our future. Not only for, we're in the United States here, not only for Americans' future strategy, but for world future strategy. This is just a partial list of the applications that I found. Automobile catalytic converters, ceramics, fluid catalytic cracking, glass additives, metallurgy, except for batteries, neodymium magnets, battery alloys, phosphors. You hit it with a little bit of energy, and out pops a photon of a different energy, the one you want, because you hit it with a known energy coming in. Percentage of total REUs used. This is in metric tons. This is in metric tons. We use a lot of this stuff. As we continue to advance with LCD screens, and now with Philips coming out with flexible LCDs and LED screens, you nevertheless have rare earths at both ends of that circuit. Look at this usage. This is almost perfectly linear. And again, it's in thousands of metric tons. We're tight on time. I want you guys to take home, rare earths are separate from the rest of the periodic table because of their F electrons. Their rare earth value stems from the tunable photonic and magnetic properties that we as scientists, me as a chemist, and physicists who mess around with condensed matter physics and solid-state chemistry just like we do, we can tune those properties. Rare earth value stems from the high magnetic susceptibilities, and that these properties are tunable in the magnetic field. I have just scratched the surface as to these applications. We have spin ices. We have Institute for Quantum Computing in Waterloo, Canada, which is working on spin ices. I actually submitted something on erbium titanates, where you can actually control the spin of this thing. You can control the quantum angular momentum of this thing and watch it bounce around a crystallographic lattice. And it's going to be used in the next 10 to 15 years to build the world's first quantum computer. That's amazing. I hope you guys understand now a little bit more about rare earth elements and what the future holds for these unbelievable materials and elements. Thanks a lot.
Stephen.
Thanks.
Thank you so much. Cool.